In this video, I'm going to talk about solving initial value problems. So I want to begin with an example. So let's say I want to solve this initial value problem. So we have this differential equation, y double prime minus 6y prime plus 8 times y equals 0. And there are these extra conditions. It tells us that y of 0 equals 14 and y prime of 0 equals 25. So these two extra conditions are called initial values because they're telling us what's happening at some initial time. In this case, they're telling us what's happening at t equals 0. And initial value problems, sometimes I will abbreviate these by writing IVP for initial value problem. So to solve this, we would begin by writing down our characteristic equation. So in the normal way that we'd begin solving one of these second order equations, homogeneous equations. So the characteristic equation would be r squared and then minus 6r. And then for the 8y term, we just get plus 8 equals 0. And now we could factor this. So this becomes r minus 2 times r minus 4 equals 0. So now we can go ahead and say what r is. So r is 2 or 4. So at this point, we're ready to write down our general solution. For our general solution, so remember, our two values of r were 2 and 4. And those were distinct real roots. So I'm going to call the general solution just y. So in y will be equal to c1 times e to the first value of r, which is 2 times t, plus c2 times e to the second value of r, which is 4 times t. So that's what a general solution looks like when we have two distinct real roots like this. Okay, but in this problem, we're not done here because we were given those initial values, and we need to use those to figure out what these coefficients are, what c1 and c2 are. So I'm going to take the derivative of this because one of our initial values involved the derivative. So taking the derivative, using the chain rule, we'd get 2c1 e to the 2t plus 4 c2 e to the 4t. And now we want to use our initial values. I want to use the fact that y of 0 equals 14, and we know that y prime of 0 equals 25. We want to use these to find the c1 and the c2. And it turns out that when we do this, we are going to be able to find them uniquely, which means there's going to be exactly one solution. So exactly one choice of c1 and c2 that'll satisfy these initial values. So why is this? Why will this be unique? So we'll talk about this in an upcoming theorem. So upcoming theorem. Alright, so let's focus on our two initial values. So the first one is, we know that y of 0 equals 14. And that's true if and only if. When we plug 0 into y, so here's y, it should be equal to 14. So if we plug 0 in for y, we'll get c1, e to the 0 is just 1. So we get c1 times 1, and then plus c2 times e to the 0, which is just 1. And that needs to be equal to 14. So now let's do the same thing for our other initial value. We know that y prime of 0 equals 25. 25. So that's going to be true if and only if. Now let's plug in 0 into the derivative. So if we do that, we get 2c1 times e to the 0, which is 1, plus 4c2 times e to the 0, which is 1, and this needs to be equal to 25. Okay, so at this point we have these two equations. We have a system of equations and two unknowns. We don't know what c1 and c2 are. So we could either do this by doing things like substituting, like isolating for one of the variables and plugging it into the other equation, or doing some sort of elimination. But since we've already developed all that linear algebra theory, why don't we use matrix methods for this? So let's use matrix methods. Although this equation is simple enough where we don't really need to. We could just solve this using basic algebra. Well, let's just practice doing this with matrix methods. So this system would become So the coefficients of C1 are 1 and 2 in the first column. The coefficients of C2 are 1 and 4. And then we need to augment that with 14, 25. So we could row reduce this to solve. Or if we could figure out the inverse of the matrix 1, 1, 2, 4, we could use that. Or we could use the inverse. So I'm going to go ahead and do it by using the inverse. But we could definitely do it by row reduction. So if I set up my matrix as 1, 1, 2, 4, that matrix is being multiplied by the vector C1, C2 to give us the vector 14, 25. So this is just writing our our system of equations in matrix form, but just being more explicit about where the C1 and the C2 are. Okay, so now let's go ahead and use the inverse. All right, so if we do that, if we multiply on the left by the inverse of this matrix, we'll be left with C1, C2 on the left-hand side. And this will be equal to, so now what's the inverse of this matrix? So it's 1 over the determinant, which would be 4 minus 2. And then for 2 by 2, we switch the roles of the A and the D, so the 4 and the 1 switch. And the other two numbers switch signs. So I'd have -1 and -2. And that would multiply the vector that we have, 14, 25. So we have this 1/2 in front. And then if you multiply this matrix times the vector 14, 25, we end up getting 31 and -3. And then if we distribute in the 1/2, we get 31 halves and -3 halves. All right, so we get that. So at this point, we know that this first term, that's C1, and this second entry, that's C2. So we are ready to write down a solution to our initial value problem. So we plug in what C1 and C2 are. So doing this, we get y equals 31 halves was C1, and that's multiplying e to the 2t. And then C2 is -3 halves, and that's multiplying e to the 4t. And that is our solution right there. If we wanted to call this YH instead of Y to represent the homogeneous solution, that's totally fine. All right, so next let's state a key theorem about solutions to these initial value problems. So this theorem says the following. If we have an initial value problem where we have this second order homogeneous linear differential equation of the form ay double prime plus by prime plus c times y equals 0 with two initial values. So we're going to say y of 0 equals some constant, capital Y naught, and y prime of 0 is going to be equal to some constant, capital Y1. This initial value problem is guaranteed to have a unique solution, so that means exactly one solution, for any choice of these constants, a, b, c, and also y naught and y1, with a not being equal to 0. Because if a was 0, this wouldn't be a second order differential equation. And moreover, the solution is going to be valid for all values of t. All right, so there's sort of two parts to this. This is saying that there is a solution. In other words, a solution exists. And the second part is it's saying that the solution is unique. There's only one. So I briefly want to talk about the idea behind each one of these and how we'd sort of show it. So to show that a solution exists, one of the ways that we can do that is talk about how do we construct a solution. But that's what we've been doing for the last few videos, demonstrating how we are going to construct a solution. So we found a solution. We found a solution using the characteristic equation. In every single case, remember, we had the three cases based off of if our roots were real and distinct, or real and repeated, or complex. But in all those cases, we were able to construct solutions. So a solution definitely exists. For uniqueness, this is beyond the scope of our class. This is something that you might see in a future course in differential equations. So in Diff EQs. So this proof is actually in the textbook, but in the expanded version of the textbook, so not our condensed version, in a later chapter. All right, so the fact that we have existence and uniqueness reminds us of linear transformations. So the fact that we have existence and we have uniqueness means that we should have an invertible linear transformation somewhere here. So I want to connect this with some linear algebra. So consequences. So there are two main consequences of this that I want to state. So the first one is, I want to put this in the context of a linear transformation. So let's say that T is a transformation that takes in solutions of our differential equation ay double prime plus by prime plus cy equals 0. And it outputs things in R2. So this is our domain right here, the solutions of our differential equation. And our codomain is vectors in R2. And the linear transformation is going to take in a function that's the solution to this differential equation, and it's going to output the initial values. It'll output y of 0 and y prime of 0. So it turns out that this function is a linear transformation. All right, and moreover, because we noted above that this should be invertible, that means that T is 1-to-1 and it's onto. It's got to be 1-to-1 and onto to be invertible. So the fact that this transformation is 1-to-1 is what guarantees the uniqueness portion of this. So we can't have two different solutions that get mapped to the same initial conditions here. So that the fact that it's 1-to-1 guarantees the uniqueness, and the fact that it's onto, that guarantees existence. Because that says no matter what vector we take in R2, no matter what two numbers that we have for these entries, there is guaranteed to be something in the domain, so a function, a solution to this differential equation, that'll get mapped to those initial values. All right, so one of the key takeaways from this, so the fact that this is a 1-to-1 and onto linear transformation, means that the set of solutions of our second order differential equation that we've been looking at, so the fact that this transformation is invertible, that it's 1-to-1 and it's onto, means that the dimension of the domain and the dimension of the codomain is the same. So when we talk about the set of solutions of our differential equation here, that's going to have the same dimension as R2 because our transformation is invertible. And the dimension of R2 is 2. And that's what we saw earlier. In a previous video, we mentioned that the set of solutions has dimension 2. And it's a consequence of this theorem about uniqueness and existence of solutions to the initial value problem. It turns out this generalizes. If I had an nth order differential equation, so something like an times the nth derivative of y plus dot 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 plus a1 times the first derivative of y plus a naught times just y being equal to 0, this would have dimension n. The set of solutions to this would have dimension n.